Hello everyone, this is Dilip. Today let's talk about a problem called overfitting that can arise in all the machine learning problems given a large test data. And we'll see how we can solve it using regularization. For now, let's concentrate only on linear regression and logistic regression. So let's take our earlier example where size of the house determines the price of the house. Let's ignore other parameters like location of the house, etc. So this is just an assumption that size of the house determines the price of the house. Now, if we take our hypothesis to be a linear equation like this, we will get a straight line that will try to fit our data. But you know, a straight line doesn't justify our picture here, because a straight line will make the price go exponentially higher for a more sized house, but it's not the case in real world. So what we'll do, we'll take a higher order. Then we'll go to a quadratic equation. And as you can see, a quadratic equation almost nicely fits our data. So it's a nice parabola kind of structure, and this fits our data. And if we want to fit all our training data into our hypothesis in any manner such that cost function is zero, it's like almost zero, it's like zero itself, then what will end up with the hypothesis is a much higher order hypothesis. Now, what kind of curve this gives us? So this gives us a curve that goes through all our data points. As you can see, it will go through all our data points. Now, this gives us the cost function that is zero for our test data, because whatever the test data we enter, we'll get the corresponding result that exactly matches the expected result. But this hypothesis is not perfect. The reason being, if you give some new data to it, it will not get you the correct result. So this has high variance. So it will keep on trying to go like this, like this, like this. So it has a high variance and it doesn't fit our data. And if we take the starting linear equation, we call it, it has the high bias, because using less number of features, and in effect the parameters we are trying to determine the hypothesis. So this problem of having high variance is called overfitting, because we are trying to fit every test data into our hypothesis. Let's move on. Now, given a higher order polynomial hypothesis like this, how do we end up with a, for example, here quadratic hypothesis fits our data well. So how do we end up with a quadratic hypothesis? So what we can do is we can penalize the parameters theta3 and theta4 such that they will become nearly equal to 0. And then our hypothesis will become like a quadratic equation. So now how do we penalize these parameters? What we can do is, given our earlier cost function, we can add 1000 times the squares of theta parameters, theta3 and theta4. And this will cause the cost function to blow up. And to reduce the cost function, the only way is make theta3 and theta4 minimal, such that their squares also will be low. And even if you multiply with 1000, they will be low. So then they will become nearly equal to 0. In that way, reducing theta 3 and theta 4 here will also cause theta 3 and theta 4 to get reduced in the hypothesis as well. And that will cause our hypothesis function to be nearly quadratic equation. So once we plot it, it won't be exactly like a quadratic equation curve, but it will be nearly equal, and that fits our data well. And let's see how do we solve the overfitting problem. So there are two ways to solve the overfitting problem. The one I said in the last slide of penalizing the parameters, and other way is remove unnecessary features. So if you are given 100 features or 200 features for a given test data, so there can be many features which are unnecessary, which you can remove by manual or model selection. This we will see in the later videos. But if we remove the unnecessary features, there is a chance that we might even remove important features. So the best way to overcome this problem is using the regularization. And one more thing is we might penalize important parameters as well. So what we do in regularization is we will penalize all the parameters. So given our cost function like this, what we do is we add one regularization parameter. About this regularization parameter, again, we will discuss in the later video. So we will add our regularization parameter lambda and then add the squares of all the parameters and multiply it with lambda. So you can see we are penalizing all the parameters. And it's beyond the scope of discussion, but you will see once you implement this, this cost function added with this regularization equation will result in lower theta values, as well as that will fit our data very much well. And let's move on. Now let's see what will be the gradient descent using the regularization cost function. As you already know, we subtract the theta parameters with alpha times the gradient of the cost function. Now, given our cost function like this, so now we have an extra added regularization equation. So given our cost function like this, what will be the derivative of j? So earlier derivative is this one. What we get is like this. And one more thing I want to note is for theta 0, like for the first parameter, we don't penalize. Even if we penalize, it's not an issue, but we usually avoid it. So the first theta 0 will be same like the gradient descent one. From the second, like theta 1 and on, what we do is we take the derivative of this cost function. And if we go further and derive it, we will get an equation like this for theta 1 till the theta n. So you can ignore the 0 here. Okay, yeah, so this is for simultaneously updating. So yeah, so we need to simultaneously update theta 0 till theta n. And as you can see, this left side will result in reduction of theta j. For example, this is 1 minus alpha times lambda by m. So there is guaranteed theta j in each iteration will at least become 0.99 times it becomes 0.99 times of theta j. So we are guaranteed that theta j will reduce. And this right side, you will see it is similar to our earlier gradient descent. Now let's move on linear regression itself for the normal equation. So for the normal equation, deriving the theta, this is the earlier equation we had for solving theta in one shot. Now, if we input our cost function, what we end up getting is the inverse what you have to calculate. It becomes a bit more calculation where x transpose x plus, it is lambda times 0, and these are all ones till the end, and rest all are zeros. And this is how we derive the normal equation method. So this normal equation method helps us in solving for theta in one swoop. So we can use a regularization also as well here. Thanks for watching the video. Bye.